Hi, I'm Elliot Aramayo, and this is my ENME 435 LiDAR project sensor. And for this project, we're going to be using a Raspberry Pi and a laser diode to make our own LiDAR scanner, which then will scan the object of our choosing. And now for our class, where we're using a camera LiDAR system, where we have the camera detecting the laser beam where it is in the frame, and the laser beam shooting out onto the object that we're mapping. So here, at closer distances, the laser appears further towards the right of the FOV, and then as we get further away, the FOV widens, so the laser appears closer to the center of the camera, its origin. Next, we'll talk a little bit about the practical applications of LiDAR. The first thing that comes to mind, for me at least, is the application of LiDAR in self-driving and autonomous cars, where cars are using multiple different systems with cameras and LiDAR detectors to scan the road ahead of them and make sure it's safe to drive. Especially like Waymo, where they have multiple systems that they're able to actually map out so that computer vision of the vehicle can see any objects or hazards in the road. Another application is with laser topography, where people are going and scanning all over the sky with planes to find things like lost civilizations and even just create maps for companies. And now the object that I chose is this metal dumpster behind the James M. Patterson building on campus. The reason I chose this is because I'm part of the Terps racing team here on campus, and I walk past this dumpster every single time that I want to go home or go to the shop. And a couple things about it is that we're only going to be able to scan 3 or 4 sides. The left side, right side, front, and the top of the lid. There's a wall behind it, and this thing weighs about probably 200 or 300 pounds with all the metal scrap in it. So our object, we're going to have to cut out the back wall. Now that we understand how the LiDAR actually works, let's talk about how we're going to do it in this class. So we're using a Pi 5 here as our actual computer, so we can take our images and then convert them to our laptop later. And we have this laser diode here, which I bypassed the Arduino by just plugging straight into the 3.3 volts and the negative. To attach the Pi, I used some really tiny M2 screws, which I did the same for the camera. So everything is held very rigidly, where the laser and the camera center are exactly 12 inches apart. Then I have it also attached to this camera base tripod here, where it's rigidly fixed, so it's standing perfectly vertically, which I can then adjust our angle so we can get our scans later on, going up and down 360 to 0 degrees. And now that our LiDAR is fully assembled, we have to go through calibrating it. So to calibrate it, we're gonna start from 0 to 10 feet. So we can see down here, I've got my measuring tape laid out, going from 0 to 10 feet over here. And as we bring the LiDAR sensor backwards more, we'll start to see the laser getting closer to the center of the camera. This is because the FOV is widening, and we'll be able to make our calibration curve based off of those alignment images. Now, the most important step that we can do is to actually make our calibration curve. So you can see in this over here, we have our sample image. This is not from the actual thing that I just did, but this is from another scan, but it's still the same concept. So now we have to adjust our HSV sliders so we can turn the red laser line into the strongest color possible. So I've already, as you can see from the text document behind our laser log calibration script, I have already determined the best colors. And this is going to make our laser line as visible as possible. So now, after determining these, we're able to run our scripts and we're able to get our calibration curve. So this is my calibration curve that I got. Another important note here is that we must adjust our rho and our RPC values. These were set to kind of random values that should be for the ideal world, but adjusting for our own, we're able to compare the curve that we made to the actual calibration curve that was given to us. And we can see here that mine fit pretty well in the range of it. I wasn't able to get as many close distance values as good, and my data was a little bit grouped further out than the actual curve. So we're out here by our target destination, which is this metal dumpster that we're scanning. I have my sensors set up such that this has been leveled to 0 degrees using the level app on the iPhone, which you can see in the picture. We're starting at 0 degrees to map down we're going to get 20 different data points going down 5 degrees each time to get a total of 20 points. I have the Pi set up here, connected with Ethernet and powered to my laptop, which I'm using Raspberry Pi Connect to take the images which will then put onto my laptop and run the Python program, run the MATLAB program to get our data points. Now that we have all of those images downloaded, we're going to have to do the steps that we did, kind of like calibration again. So that means we're going to have to redetermine our HSV colors, which I've done here. And then once we run the script, we're able to finally produce the text file that will let us open in MATLAB to view our point cloud, and then later we can open that and also cloud compare. So here I have my MATLAB script, and here is the results of my first mesh. So we can see here that we've captured a lot of good details of what we want, and this is a very good result. We can see the fine details such as the handle on the top and the little pop-outs on the sides here for forklifts and the feet on the bottom. Next up was to complete the scans of both the left to the right side and the top lid. So after doing that, doing the same thing, changing the HSV values, acquiring data, then making the text file, we were able to get these 4 different individual point clouds. So now all we have to do is rotate and get everything into order. And now here we have our final model all put together. So we can see that we got some really good detail capturing on the front, but the sides a little bit more rough. It was also not possible to record an actual scan of the back because it was pressed against the wall. And additionally, I had to take scans on different days where there were people who parked their bikes to the side and I had to push them out of the way. Overall, this mesh came out really good.